Okay, so for 4.6, we're going to do related rates. And so here's example number 1 of related rates. So 4.5 was kind of you know, with the linearization method and all those things, 4.5 was kind of getting us ready for this related rates. With the second part of the examples where we do the differentials. And so for example 1, let me read it to you guys and then we'll go through and do the problem. It says, assume that the radius of a sphere is a differentiable function of t, and let v be the volume of the sphere. Find the equation that relates dv dt and dr dt. And then the second part of that is, assume that the radius r and the height h of a cone is differentiable functions, and then we do the same thing. So what they want us to do is they want to make this kind of a function of time, okay? So we have the volume of a sphere is equal to 4/3 pi r cubed. Oops, r cubed. And so this is not that hard. They want us to differentiate with respect to time, right? So that's what they mean by dt. So what we're talking about is like, maybe you have a spherical balloon, like a weather balloon, and you know what the rate of change in which the radius increases over time. You know, you would want to make some comparison to how much the volume of the balloon increases over time. So here when we differentiate, we're going to differentiate d dt, and we can do that. So what does that look like? Well, we just have dv dt here, which is equal to, now the 3 gets tossed to the front. These are all constants. Oops. These are all constants. And so those just pretty much remain the same, but by using the power rule, I've got to toss the 3 to the front. So technically I've got 3 times 4 over 3, and then tack on the pi, and then this is r squared. And so the 3's cancel, and I get 4 pi r squared. Now, I don't know if you guys remember that. Does anybody know what that formula is off the top of your head? Take a guess. Anybody? Anyone? I think it's the surface area of a sphere, isn't it? Yeah. So that's not an accident. All right. So anyways, but we took the derivative with respect to t, so I've got to tack on dr dt. Okay? Now if I were to tell you, now this is how these problems are going to work. This is not what we're asked to do in example number 1, but here's how these problems work. The radius increases 1 unit per second, right? So that would be my dr dt. The radius increases 1 unit per second, or 2 units per second. So if the radius is measured in feet, it increases 2 feet per second. So then they would say, what would the change in volume be? And I would plug in dr dt right here and multiply it, and that would give me dv dt. Does that make sense to you guys? Now let's do that again one more time with the cone. So part B of example number 1 said, do the same thing with the cone, but now we're going to introduce a third variable. So here they want the volume of the cone. So let's start with the formula for the volume of the cone. Well, the volume of a cone is similar. It's pi over 3 r squared h squared. And so we're going to take the derivative with respect to time, because that's usually what we use it for. It's just saying the d dt. But that's what we're, the practical application of this would be. Now here, it gets a little tricky because, well, first of all, we have one constant, so that's going to get tossed to the front. And then I have to apply the product rule for r squared and h. And over here, it's real simple. It's just dv dt. But this is a little tricky. So in order to apply the product rule, I gotta do it like this. So remember that if we say uv and we want to take the derivative of that, it's usually something like uv prime plus vu prime. All right? So this is the weird thing. So basically what I'm gonna do is I'm gonna say r squared, right, times the derivative of h, which is just what? 1, but I have to tack on dh dt, because we're taking the derivative of h with respect to t, plus, now I'm going to say h times the derivative of r, which is just 2r, but I have to tack on the derivative with respect to t, which is dr dt. And I suppose if you wanted to, you could clean it up a little bit. We would say that the change in volume with respect to time is equal to pi over 3 r squared dh dt plus 2 hr dr dt. So in this particular case, and when you think about the cone, it could expand several ways, right? So the cone's height could increase, and that could have a different rate of change, and the radius could increase, and that could have a different rate of change. All right. Now you would say, well, how would the height increase and the radius increase? Usually, this is like sand. Like these problems are usually set up like sand pouring out of something. So like if you have sand and it's pouring out of something, it forms a little cone. And as more granules of sand fall on the pile of sand, it's shaped like a cone. In other words, the radius will increase at one rate, and the height also increases. So you can calculate the volume of the sand with this process by plugging in 2 of the 3 rates of change, right? Because in this case, the volume is dependent upon the radius changing and the height changing. Does that make sense? Any questions on this one?